Previously, we looked at independent samples between the means of two different samples, and now we're going to look at dependent samples. Dependent samples are ones in which the pairs are connected, so they may be a matched pair, such as husband and wife, or they may be a temporal pair, such as before and after. The test statistic for two means of dependent samples: both samples have to be simple random samples. Samples should be large. N1 and N2 are greater than 30, and the pairs of values have differences that are from a population having a distribution that is approximately normal. We need to find the individual difference between the two values in a single matched pair. Then we need to find the mean of all those differences. And then what we'll do is the D bar, that's the mean of all the differences in the sample. We will use that to make our judgment about the population mean of all the differences for the pairs of data. And then we also have the standard deviation of the differences for the paired sample data. So please note that these two refer to the sample, and they're the same kinds of things that we've done in the past for finding the mean and the standard deviation. Here is our test statistic, and again, you should recognize the form. All that's being changed is, in fact, that we're using D bar. In the past, we would have had X bar for the mean of the sample. Here it's the mean of the differences. And then we have the standard deviation of the differences, and again divided by n, degrees of freedom n-1. Again, all of this should look fairly similar to what we've seen before. It has just been altered or modified slightly for this particular situation. Likewise, if we want to make a confidence interval, that is very similar to what we had before. It's just that the standard deviation in this case is the standard deviation of the differences of D for the paired sample data. So, I want to emphasize that really the steps for all of these hypothesis tests are going to be similar to what we've seen before. It's the same steps that we've been doing all along. The only difference is, we've modified an equation here or there, and the situation is different, but we're really doing the same steps. It's really the same approach. So, we're going to look at a table, lists results from the study of the measured weights of college students in September and April of their freshman year. Use a 0.05 significance level to test the claim that for the population of students, the mean change in weight from September to April is 0. So, here is our sample. Now, we do have two random samples. They are dependent. It's the before and after case. It's not truly a simple random sample because the students volunteered as opposed to randomly selecting them, but we're going to assume that it's close enough. It is a small sample, but there are no outliers, and the sample is approximately normal. Now, this is the same one, but we're going to first start off the same table we looked at before. I just wanted to put it onto the next page so we could go back to it if we wanted to. We're going to start off with the traditional method. Remember that the traditional method is one that will compare, in this case, t-scores. And so if the test statistic falls outside of the critical value t-score, then we would reject the null hypothesis. If it is inside or less than the critical t-score, we would fail to reject the null hypothesis. So our claim is there is no difference in fact, that the mean difference between April and September was 0. So our counterclaim, not equal to. Remember that the null hypothesis always gets the equal sign, and in this case, the alternative got the not equal to. Alpha is 0.05. We have dependent samples. We're going to use the t-distribution. Now, before we can actually find the test statistic, we've got to do a little bit of pre-work. Find the mean of all the differences, find the standard deviation of the differences. If we add up all our differences that we have listed here, -1, -1, 4, -2, and 1, It adds up to 1. There are 5 of them, so 1 divided by 5 gives us d bar is 0.2. If we go ahead and do the traditional standard deviation we've done before, d minus d bar for each of these cases, square it, divide by 4, 1 less than the 5 samples, we're going to end up with a 2.387. Now, since we have all of these things, we can go ahead and find our test statistic. Note that mu d is 0. That is our null hypothesis, so that's why we put the 0 in there, and we end up with a test statistic of 0.1874. Now, the fact that in our alternative hypothesis we have a not equal to, that means it's two-tailed. So we are looking alpha 0.05, degrees of freedom 4, two-tailed, table 5, and we get a critical t-score of plus or minus 2.776. So the critical region is less than t equals negative 2.776 or more than t equals plus 2.776. So it has to be outside of those values. Okay, our comparison step 7. Since the t-score equals 0.1874 does not fall in the critical region, in fact it's less than our 2.776, we fail to reject the null hypothesis. So in fact it could be that the mean difference is 0. And our conclusion, there is not sufficient evidence to reject the claim that the mean change in weight is 0. Now, if we wanted to do the confidence interval method, of course the first 5 steps would all be the same, and we would do the same work for finding d bar, the standard deviation, and the t-score. All of that would be the same. We would just have to find the margin of error in this case. And so 2.776, the same one that we got up there, 2.387, the same one that we got over there, divided by square root of 5, and that gives us a margin of error that is approximately 3. So our confidence interval, d bar minus e, d bar plus e, we end up with our mean difference for the population should be between negative 2.8 and 3.2. Since mu d falls within the confidence interval, we're going from negatives to positives, so 0 has to be in there. We fail to reject the null hypothesis. We can't say that mu d equals 0 isn't in fact true. And again, there is not sufficient evidence to reject the claim the mean change in weight is 0. And so that's all we're going to do for this section, because again, we're really doing the same thing that we've done in a number of cases. The main purpose of this example is so you can see where the different equations fall.